Okay. So perpendicular lines, let's see, go to page 172 and let's see if we can learn how to draw a perpendicular line first. So if I'm given a line segment that looks like this, okay, I can take my compass again, my handy dandy compass, and I would go ahead and go like this, and I will draw like that. I would take the same one and I would draw like this all the way through like that. Okay, so now I've created two points here. Now if I connect these, okay, this is supposed to be perpendicular. Okay, not only is it perpendicular, actually this line and this line are going to be congruent, okay? And the reason being is that, well, this is what we call this a perpendicular bisector, because not only is it perpendicular to this line, it cuts it in half, it bisects it, okay? And the reason being, if you were to draw this shape, what shape is this? Can anybody tell me what shape this is? Because I will tell you that all four of these lines are the same length, right? This length, this length, this length, this length are all the same, right? So what is this? What is this? What kind of shape is this?
A square.
Okay, it could be a square. This one looks like a square, but it really doesn't have to be a square, right? It could be a square that's a little bit squished, right? If I took a square and I squished both sides of it, in other words, if I had a square that looks like this and I squished it, it's going to look like this, right? Where I still have the same size, right? The same sides. What is this called? Does anyone remember doing this in pre-algebra?
A rhombus?
It's a rhombus, exactly. It's a rhombus. One of the characteristics of a rhombus is that the diagonals are perpendicular to each other and they bisect each other, okay? All right, and we'll discuss that later on in further chapters, but okay, just a preview there. Okay, and that's why this line becomes a perpendicular bisector, okay? So that's how you draw a perpendicular bisector line, all right? Now, let's go to example number one. Example number one, distance from a point to a line. Example number one. Name the shortest segment from P to AC. So if I have AC and I have point P here, the shortest distance from here is going to look like this, right? And it's actually going to be a perpendicular line, right? Okay, so that would be the shortest line, okay? And now it gives us, in B, it says write and solve an inequality for X. So if I went like this, and this was 5, and this was X plus 3, okay? We'll call this, what do they call this? They call this B, okay. If you look at triangle A, B, and C, right, or A, P, B, you're gonna have a 90-degree angle here, right? So we know that the hypotenuse is going to be longer than PB, this leg, right? Because the hypotenuse, by definition, is the longest leg, right? Therefore, you have, right? If you have C squared is equal to A squared plus B squared, right? A squared plus B squared is equal to C squared, right? Which means that C squared has to be larger, C has to be longer than A by definition, right? Okay. Also, it makes sense, right? If you go from here and you move it out, as you move it out, this leg is going to get longer and longer. It's actually going to be greater than 5, right? It has to be greater than 5. So in other words, X plus 3, this guy here is always going to be longer than 5, Okay, so this is the inequality that they're talking about. If you move the 3 over, you get x is greater than 2. Okay, there you go. That's that. On top of page 173, again, we have a bevy of theorems there. Let's see if we can read those and see if it makes sense to us. 3.4.1, if two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. Okay, the key word there being linear and congruent. They're congruent, which means that they're the same, and they're linear, which means they have to add to 180, right? If two same angles add to 180, obviously each one of them have to be 90 degrees. Okay? 3.4.2, perpendicular transversal theorem. In a plane, if a transversal is perpendicular to one of the two parallel lines, then it's perpendicular to the other line. Well, that makes sense, right? If I have two lines, right, and I cut it with a transversal and this guy is 90 degrees, okay, then what? Okay, and they're parallel lines, that means that this guy has to be 90 degrees also. Why does it have to be 90 degrees? Anybody tell me? What are these two angles called?
Parallel angle? Oh, right angles.
Well, they're right angles and they're parallel. No, what are these two angles called in a transversal? They're corresponding angles, right? They're corresponding angles, right? So since it's parallel, the corresponding angles have to be the same, which means that if this is 90, this guy also has to be 90, right? 3.4.3, if two coplanar lines are perpendicular in the same line, then the two lines are parallel to each other. Okay, that's just the exact converse, right? If I do this and these two are 90 degrees, that means that this has to be parallel. Okay. Okay, so that's that. We kind of did the proof already, so I don't have to do that. Let's go to example number 2. Example number 2, write a 2-column proof given that, okay, so we're given that AD and BC are parallel. So I have 2, and I have, this is A, B, C, D. Okay, given that AD and BC are parallel, AD and BC, these two lines are parallel, okay? And AD and AB are parallel to each other. AD and AB are perpendicular to each other. And BC and DC are perpendicular to each other. Prove that AB and prove that these two lines are going to be parallel, right? Okay, so how would you prove that? Again, I don't have anything that governs these across like this, right? But I do know that since this is parallel, and this is a transversal, and this is, if this is 90 degrees, this guy has to be 90 degrees, right? And that was 3.4.2, right? Okay, so I know if this is 90 degrees, this is 90 degrees, but I also know that this guy and this guy is both 90 degrees, right? Therefore, this transversal, okay, is cutting two lines that have both 90 degrees. Therefore, this line and this line are parallel. Okay, so that would be the proof. Okay. Example number 3. Let's move on to example number 3. Example number 3, oceanography application. Rip currents may be caused by a sandbar parallel to the shoreline. Waves cause a buildup of water between the sandbar and the shoreline. When the water breaks through the sandbar, it flows out in a direction perpendicular to the sandbar. Why must the rip current be perpendicular to the shoreline? Okay. Well, basically, you have the sandbar and you have the shoreline, right? You use shoreline. And this is the sandbar. And we are told that these two are parallel to each other, right? It says that the sandbar and the shoreline are parallel, right? So what it says that, so what are we trying to prove? Where why must the rip current be perpendicular to the shoreline, okay? So this is the rip current, if this is the rip current, okay? I guess it's two words, right? Rip current, okay? And then we are told that this is 90 degrees, okay? So the question is, why does this have to be 90 degrees also? Well, it's because these two are parallel, right? And this is a transversal, that means they're corresponding angles. So if this is 90 degrees, this guy must be 90 degrees also. Okay? All right. Any questions? Any questions of what we talked about?